In this lecture, we explore the TypeScript language features that let us implement abstract data types cleanly and precisely. We cover interfaces, factory functions, subtyping, generics, and enumerations. By the end of this session, you should be able to define ADTs using interfaces and explain their advantages over classes alone. You should understand factory functions, the Liskov substitution principle, structural subtyping and its pitfalls, generic interfaces, enumerations, and getters. These are the core tools for building software that is safe from bugs, easy to understand, and ready for change. A TypeScript interface is a list of method signatures, no method bodies, no fields. The myString interface declares three operations: length, charat, and substring. It says nothing about how they are implemented. A class like SimpleMyString uses the implement's keyword to declare it satisfies this contract. The key insight: the interface defines what. The class defines how. Clients read only the interface. They are completely shielded from implementation details. Interfaces offer several advantages over using classes alone. First, pure contract separation. Clients read only the interface with no implementation noise. Second, no rep exposure by design. Interfaces have no fields, so clients cannot create dependencies on any internal representation. Third, documentation for both the compiler and humans. Every implementing class is statically checked to provide all required methods. A missing method is a compile error, not a runtime surprise. The interface is the abstraction barrier enforced by the type system. Interfaces also enable multiple representations to coexist. Simple, myString and fastMyString both implement the same myString interface. They can exist in the same program simultaneously. Simple myString might be simple and easy to verify as correct. Fast myString might be faster but more complex. You can use the simple version for testing and the optimized version in production with a single line change in one factory function. Clients never need to know which implementation they are using. Interfaces have specific constraints you should know. They cannot contain private instance variables, method bodies, or AF and RI comments, because they have no rep to describe. They also cannot be instantiated directly. Writing new myString will produce a compile error. You must instantiate a concrete implementing class, but we will see a much cleaner solution: the factory function. Here is the complete myString interface. Length returns the number of characters. Char returns the character at a given position with the precondition that I is a valid index. The substring returns a new myString covering the range from start to end with its own precondition on the bounds. Notice how the spec is written entirely in terms of the interface. Clients need nothing beyond this. Two very different implementations can satisfy the identical interface. Simple. myString uses a uint16 array storing every character code. When you call substring, it copies the relevant portion into a new array. fastMyString also uses a uint16 array, but it stores only a start index and an end index into a shared backing array. Calling substring just records new indices, no copying at all. For substring-heavy workloads, fastMyString is dramatically faster, but both satisfy the exact same myString spec. Clients cannot tell them apart. If a client writes new fastMyString directly, they have broken the abstraction barrier. Their code now depends on the concrete class name. If we rename fastMyString to optimizedString, their code breaks. If we switch to a new implementation entirely, every constructor call must be updated. Clients should reference only the myString interface, never the concrete classes. But how do they create instances without knowing the class name? That is exactly what the factory function solves. A factory function is a regular function that creates and returns an instance of a concrete class, but returns it typed as the interface. MakeMyString accepts a string and returns a myString. Inside, it uses fastMyString, but clients only see the return type myString. The factory function is the only place in the codebase that mentions the concrete class name. Switching implementations from fastMyString to optimizedString or to a third implementation requires changing exactly one line in exactly one place. When is one type a subtype of another? B is a subtype of A if every B is an A, meaning B's specification is at least as strong as A's. This is the Liskov substitution principle. A subtype may strengthen postconditions, guarantee more than A does, and it may weaken preconditions, accept more inputs than A requires. But a subtype must not weaken postconditions or strengthen preconditions. Doing so would make B a less reliable substitute for A. TypeScript provides two keywords for declaring subtypes. Implements declares that a class is a subtype of an interface. The compiler verifies every method signature matches. Humans must still verify the specs are honored. Extends on an interface declares that one interface is a subtype of another. Sorted. Set extends mySet, inheriting all of mySet's signatures and adding a new min operation. Sorted set is a stronger contract than mySet. It provides everything mySet does, plus ordering. TypeScript uses structural subtyping. B is a subtype of A if B provides all the operations A requires, even without an explicit implements A declaration. The standard array type is a structural subtype of read-only array because array provides all the observer methods that read-only array requires. This means you can assign a mutable array to a read-only array variable. The TypeScript compiler permits this. But there is a dangerous edge case hiding here. Structural subtyping has a hole. You can keep a mutable alias. Assign a mutable array to an immutable read-only array variable. Then mutate through the original mutable reference. The supposedly immutable variable now reflects the change. Array is a structural subtype of read-only array, but it is not a true subtype in the spec sense. Array's contract does not provide immutability. Mitigation: discard all mutable aliases immediately after assigning to a readable type. Do not keep both references alive. How does subclassing differ from implementing an interface? When class B extends, AB inherits both method bodies and the internal state. The subclass can access protected fields. Changes to A's implementation can silently break B. When class B implements IB inherits only method signatures. There is no rep to inherit, no protected fields to accidentally misuse. Prefer interfaces over superclasses wherever possible. The risk of accidentally violating a superclass's invariant through inheritance is significant. When you extend a class rather than implement an interface, the superclass must maintain two separate contracts. One contract for clients, the public API, and one contract for subclasses, the protected API. Writing both correctly is hard. The subclass can inadvertently reach into the superclass rep through protected fields and corrupt its invariants. This is why composition over inheritance is a common software engineering principle. Wrapping an object is safer than extending it. Two terms are easy to confuse: overriding and dynamic dispatch. Overriding a subclass replaces an inherited method body with its own implementation. Dynamic dispatch at runtime, TypeScript selects which method body to call based on the dynamic type of the object, not the static type of the variable. In this example, S is declared as myString, but it actually holds a fast myString. Calling s.toString dispatches to fast myString's toString, not to some default. Dynamic dispatch is the mechanism that makes polymorphism work. Static type and dynamic type are determined at different times. The static type is determined at compile time based on the variable declaration or type inference. The dynamic type is determined at runtime based on which constructor was actually called. In our example, X has static type imList of number, but its dynamic type is empty of number. The compiler uses static types to verify that operations are always valid. The runtime uses dynamic types to dispatch to the right method implementation. A generic type uses a type parameter, a placeholder filled in at usage time. The mySet interface uses element as its type parameter. mySet of string, mySet of number, and mySet of date are all valid instantiations. The interface is written once, but it works correctly for any element type. By convention, type parameters use capitalized names: element, T, K, V. Generics are how we write truly reusable, type-safe data structures. Here is the full mySet generic interface. .size returns the number of elements, has checks, membership. Add modifies the set by inserting an element. These specs are written entirely in terms of the abstract notion of a set. They say nothing about how the set is stored. They apply equally regardless of whether element is a string, a number, or a custom class. A concrete, non-generic class fixes the type parameter to a specific type. Digit set implements mySetOfNumber. It stores digits 0 through 9 using a Boolean array, index 0 for 0, index 1 for 1, and so on. Size counts the true values, has checks the array, add sets the entry to true. Digit set is efficient for its specific purpose, but it cannot hold anything other than single-digit numbers. A generic class keeps the type parameter open. It works for any element type. HashSetOfElement implements mySetOfElement. It stores items in a plain array. The implementation cannot assume anything about element beyond what the interface specifies. It cannot call methods specific to numbers or strings on the elements. It can only use the operations guaranteed by the element contract. This is the power of generics. You write the implementation once, and the type system enforces correctness for every element type. Generic functions provide type safety without committing to a specific type. AssertDefined accepts a value of type T or undefined and returns T. If the value is undefined, it throws. The return type narrows from T or undefined to T. No typecasts needed. No non-null assertions. The type system carries the narrowing forward automatically. The caller knows the result is defined. An enumeration defines an ADT with a small finite set of named immutable constants. The month enum has 12 constants, January through December. The direction enum has 4 constants with explicit string values. Static checking. The compiler prevents assigning a direction where a month is expected, no magic numbers, no typos, no wrong type values. Enums are one of the simplest and most immediately valuable features in TypeScript. TypeScript supports 2 flavors of enums. Numeristic enums assign implicit integer values starting from 0. Month.februre prints as 1. String enums assign explicit string values. Direction.east prints as east. Use string enums when the value appears in logs, serialized data, or error messages. Reading north in a stack trace is far more helpful than reading to. Why use enums at all? 3 reasons, 1 for each of our core goals. Safe from bugs, the compiler rejects any value not in the enum, no magic number 14 slipping in as a month. Easy to understand, month.December is immediately clear, the integer 11 is not. Ready for change, if you rename an enum constant, the compiler finds every usage and flags it as an error. No silent breakage. Whenever you have a finite set of values, define an enum. The few minutes it takes pay off immediately. Getters let an observer look like a field to clients while hiding computation inside. FastMyString stores a start and an end index. The length is computed as end minus start. With the get keyword, clients write s.length, identical syntax to accessing a stored field. This is the ready for change benefit in action. You can switch between a stored field and a computed getter at any time without changing any client code. Data abstraction is a universal design principle that predates object-oriented languages. In C, the standard phi type is completely opaque. Clients cannot see its fields. They can only use fopen, fred, fgetC, and a close. This is representation independence without any class or private keyword. The interface has 4 named operations. The implementation is hidden behind a pointer to an opaque struct. The pattern matters. The language is secondary. Here is a summary of the TypeScript ADT toolbox. Abstract types are expressed using interface, class, and enum. Creators are constructors, factory functions, and enum constants. Observers, producers, and mutators are all expressed as instance or static methods. Getters provide observer access with field-like syntax. The rep is stored in private fields inside the implementing class, invisible to clients. To conclude, interfaces formalize ADTs as sets of operations, giving clients a clean contract with no implementation noise. Generics create reusable, type-safe families of data structures that work for any element type. Enumerations provide safety and clarity for finite value sets. And subtyping enables flexible design, but structural subtyping requires discipline to avoid type safety holes. Together, these tools produce code that is safe from bugs, easy to understand, and ready for change.